Muy buenos días a todos. Good morning, everyone. Estamos muy contentos de recibir el día de hoy al doctor Ahmed Chimoy, que nos acompaña gracias a las gestiones del Consulado de Francia aquí en Monterrey y de la Embajada de Francia aquí en México, después de un convenio que celebramos en días recientes. Y inmediatamente, pues, corazón, gracias también por sus gestiones y por la disposición. Welcome, Dr. Monterrey, for your visit. I hope you feel like you're at home, and we're very pleased to receive you today. Decirles que hay una gran experiencia puesta a disposición, queremos aprender de los mejores, y él es uno de los mejores en su campo en temas de dispositivos médicos, en el tema de exoesqueletos y otras cosas más. El currículum no se lo vamos a leer, le toca presentarlo a Emma, son más de 35 páginas. We're talking about, you have 35 pages of interesting, and we're not going to mention everything. And we're going to make a short presentation about that. But it did not make justice of what this man has been doing in his research, and he's going to share with us. And we hope a lot we can learn about your experiences and all your knowledge to us. We're very helpful to be here today with you. And sin más palabras, sin más, les damos la bienvenida y le cedo la palabra a Emma para que presente el currículum del doctor.
Gracias, buenos días a todos. Antes de comenzar, quisiera nada más hacerles un recordatorio de que los micrófonos ambientales junto a están prendidos. Son bastante potentes, entonces se escucha todo lo que decimos, incluso desde nuestros acentos, para que tengan esto. Good morning, doctor. Thank you very much for coming all the way to Monterrey to this conference. I have the honor to read your biography. Resume. Dr. Ahmed Chimoy is a senior researcher at the French National Center for Scientific Research, specializing in automatic control and robotics at the Laboratoire d'Informatique, de Robotique, et de Microelectronique de Montpellier, in France. He earned his PhD in automatic control from the Grenoble Institute of Technology in 2005. His work focuses on non-linear control, adaptive, robust, and predictive, and its application to underactuated, parallel, underwater, humanoid, and wearable robotics. He has published over 180 scientific papers and has supervised more than 60 master's and PhD theses. He serves as a technical editor for the IEEE transactions on mechatronics and as an associate editor for Frontiers in Robotics and AI. He is actively involved in several technical committees of the International Federation of Automatic Control, including those for mechatronic systems, robotics, adaptive systems, and marine systems. Dr. Chimoy has been a visiting professor at institutions across Europe, Asia, and Latin America, and a plenary speaker at numerous international conferences. His work bridges theoretical research and experimental validation, contributing to the advancement of robotic systems for industrial, medical, and marine applications. We look forward to hearing your conference, Assistive Control of Wearable Exoskeletons for Rehabilitation Purposes. Thank you.
Thank you very much, and it's my pleasure to be with you today to go this workshop, this short workshop, since it is just 2 hours, and I will try to focus the outline of the presentation of today about assistive control of wearable exoskeletons. First of all, before I start talking about the topic itself, let me introduce my institution. So as they said, I am coming from Montpellier. Here, as you can see, this is the map of France. So Montpellier is a city situated in the south of France. Very nice city, as you can see from the pictures. Here it is the center of Montpellier. And Montpellier is known by 12 things. I will just mention 2 or 3 things. First of all, we have, according to the statistics, we have more than 300 sunny days during each year. We have very nice beaches. It's the 8th biggest city in France with more than 300,000 people. And our University of Montpellier, we have more than 70,000 students. And Montpellier also, it's known by something else. We are talking about health and so on. So just to know that the first or the oldest faculty of medicine situated in Europe and maybe in the world, it is situated in Montpellier. So it was founded around like 1220. So we have a strong field in medical robotic, medical staff in Montpellier. So with strong hospitals and institutions also. I am working in a research lab called IRM, and IRM, as you can see here, this is the abbreviation, so it's coming from Laboratory of Informatics, Robotics, and Microelectronics of Montpellier, situated in the north of the city. We have 2 buildings. This is the old building, this is the new one. And actually, as any research lab in the world, our laboratory belongs to the university, which is the University of Montpellier, as you can see here. However, something which is specific in France, we have another big research institution which is called CNRS. It's the biggest research institution in France and Europe. And we have a lot of research labs in all the countries. And our laboratory belongs also to this research institution. It means that in this research lab, we are a mixture of faculty members employed by the University of Montpellier and CNRS researchers like me, working in CNRS. Our laboratory is organized, as the name indicates, in 3 departments. So the first one, which is the biggest one, almost half of the lab is the laboratory of computer science, with almost like 20 research teams. And also the 2 other departments is the Department of Robotics, where I'm working, and the Department of Microelectronics. So this is a clear organization of the lab. And now let me just tell you a few words about my research activities. Because actually I will talk just about exoskeletons, but I'm working on much more applications in robotics. So the heart of what I'm doing is situated here in the middle. I'm working on control of complex robotic systems. So this is the main topic I'm working on. So I am from control community, and I did my PhD in Grenoble on control of bike-walking robots. And when I came to here, I started working, I continued working on control of robots, but now I try to enlarge the spectrum of applications such that you will see the applications that are around here. So the first application is concerns parakinematic manipulators. We can find 2 kinds of robots. This one is called the platform of Stewart, and mainly it's used for flight simulators, for instance. And the second kind of robots is the lightweight robots, like Delta robots that you can see here on the second picture. And those robots, they are used mainly for high-speed pick-and-place applications for food packaging. As you can see, the application here is chocolates packaging. You take the chocolate and put it in a box, and you repeat this operation as fast as possible. And the research topic that I'm working here is to design controllers to guarantee the control of those high-speed robots. The second application is concerns the control of unactivated robotic systems. So in a robotic system, it has a certain number of degrees of freedom and a certain number of control inputs or motors. So if your system has less control inputs than degrees of freedom, so it is underactivated. And the question is how we can control a certain number of degrees of freedom with less degrees of freedom in the control, less control input. This is the challenge concerning the second topic. So the third topic is concerns in marine robotics, and here I am interested mainly in 2 kinds of underwater vehicles. So the first one is classical conventional propeller activated by underwater vehicles, and the second class is the class of bike-inspired underwater vehicles. And as you can see, you have one example where the robot is actuated with fins instead of classical propellers, and we did a lot of works like for the cooperation between the robot and the human on diagrams. So this is the third one. The fourth application concerns the control of walking robots. And for walking robots, I worked a lot on humanoid robots like that for walking aid control. And recently I started with the cooperation with Estonia working on the control of this kind of robots in extreme conditions. I mean, controlling the robot walking outside in mud, for instance. And the last topic is the topic of the presentation I have today. So I will develop this topic in the forthcoming slides. So this is the outline of the presentation of today. So we just start with the introduction of the context. The context of exoskeletons. Why exoskeletons? What are exoskeletons? Where they are used? Some basic definitions and main applications where these exoskeletons are used. Then I will try to show you also a brief historical overview. So it started very long time ago, development of this kind of systems and some examples of exoskeletons of today, and even those who are sometimes commercialized in recent years. Then I will talk about my experimental setup. We have different exoskeletons. I will focus on one. It's for the knee rehabilitation exoskeleton. Then I will try to develop or detail just two control input to two control schemes. First one is an L1 adaptive control, and the second one is a mother predictive control. And these two control schemes have been used to control an exoskeleton for rehabilitation. Then I will show you some real-time experimental results for each one of these two control schemes, and I will try to include the presentation. Let me show you one video just to start.
For paraplegics who have experienced profound spinal cord injuries or other neurological disorders, wheelchairs may have been the best means of mobility. Now, researchers are focusing on exoskeletons, robotic ambulation devices, as a therapeutic intervention that may help some paraplegics get on their feet again. Let's take a look at some of the options currently being developed. 4 types of lower limb exoskeleton devices are currently being used in research and clinical trials, including the Exo by Exobionics, Indigo by Parker Hannifin, Rewalk by Argo Medical, and Rex by Rex Bionics. These devices offer upright mobility to injured people who are unable to walk or who can walk only for limited distances. Early research suggests that these devices can contribute to reducing medical complications and improving physical strength and emotional wellness. In the meantime, it's critical for paraplegics to pursue habits that may allow them to qualify to use these devices, including maintaining a healthy weight. While clinical trials continue, exoskeleton manufacturers are pursuing approval for private purchase of these devices in the United States. For more information on exoskeletons, view our recent webinar at paradigmcorp.com/webinars. You can also connect with us on Facebook and Twitter.
Fine. So now let's introduce the context or the general context of exoskeletons. So to do that, let's be talking about some issues that we have in our society of today. So the first issue that we want to mention, as you can see from this picture, is the issue of elderly persons or the aging of the population all over the world. So this is one issue, and you have to take account this issue when we develop technological solutions. We have to take care about those persons. I will say more details in the following. Second point that I want to mention, despite the automation, despite the level of automation that we reach today, development of robotics, autonomous systems, automation, and so on in many domains, we still have a lot of work done by workers. So they are very dangerous for their health because of the posture, because of the work itself, because of the numbers of hours, and a lot of things. So this is one issue. And let me also mention a third issue of today. Also, 2025, and we still have some wars in some places of the world, and this is also the issue. And the last issue that I want to mention, despite the development of autonomous vehicles, very well developed and autonomous and very technological development applied for vehicles, we still have traffic accidents. So if we sum up all those four issues, what would be the consequence? So the consequence of the four issues that we have an increasing population of aging people all over the world, in all the countries that we have this tendency. Workers with a lot of problems of health, elderly persons, disabled persons, and so on. And the question that we may ask when we look to these consequences is what we can do, what we can develop as a technological solution to help those persons. So this is the question that we may ask. Now let's focus on the first issue, the issue of aging of the population, as you can see here. So I took just a report from the United Nations concerning the world population aging, and here is a summary of the content of this report made by the United Nations. Here you have some countries, mainly in Europe, like France, Germany, Italy, and UK, and you have here the years starting from 1950, and you can see here the progress of the population over 65 years old. So without any extension in all the countries, we can see this evolution and this increasing of the population of the aging people. So this is a real issue. Then let me give you the map of the world just to show how the extent of this issue all over the world. As you can see here, it's around 2000, and you have some colors here, and the colors it represent the percentage of the people who has 60 years, more than 60 years old. And if the color is dark, it's becoming dark, it means that this percentage is higher. And as you can see here, depending on the countries, like for North America, like Europe, and some places of Asia, we still have like a big population. But now let's see the progress. This is just in 2000. Look to the progress, 2015, and the colors they are becoming darker. And there is a projection like around 2050. And in 2050, as you can see, look to the change of the colors between 15 and 50. And as you can see, we have much more people with 60 years old or more all over the world, and this is a big issue. So to deal with this issue, these people they become more and more dependent. They will have a lot of problems, or a lot of problems of health, a lot of problems of obesity, a lot of problems summarized here. And the question is that we can ask concerning our case, or our research topic. What will be the solution for their mobility problems? How we can help those people in terms of mobility? Pay attention. Maybe you cannot realize at what level those persons they need help. I give you just a very simple task. I mean, if you have a human and you are in a wheelchair like that, in a chair like that, and you move from seat to stand, you are in sitting position, you go to this. For us, it's very easy. We don't think for us, it's very easy. But for an elderly person, this may become a challenge. Just doing this motion from seat to stand, it's become really a challenge. They cannot do it. And this, because of the weakness of the muscles in the legs, they cannot do this. So this is a big issue. So in this case, exoskeletons may be a solution. So this is why I'm talking about this topic of today. And here, as you can see, an illustration of this task of sit to stand using an exoskeleton that can be used to help the humans to do this task. Nice. Before going further and talking about my research and activities, let's go back to the basics. I don't know if all the people here, they are specialized in exoskeletons or no, but this is like some basic definitions. So the first thing to know, what is an exoskeleton? Because an exoskeleton is a robotic system used within by the human and so on. So from where we have this definition of an exoskeleton? Before introducing the term of exoskeleton, let's talk about something else. Because actually, if you see the human and animals, what we have inside our body, it's not an exoskeleton, it's an endoskeleton. And the endoskeleton is here to protect the body, the body and support the inner working of the body. And here we have muscles attached to the exoskeletons, and then using the muscle, you can move the different limbs of the body, and you can do the tasks of daily life. Then, if we look to the animals, we have something else. So the animals like insects, like as you can see, some examples like spiders, like shrimps, crabs, and so on. They do not have they do not have endoskeleton. So they have something outside the body, and we call it exoskeleton. It's something to protect their body, and it's used to move to protect their body from the predators, for instance, and so on. And we have the exception, we have one animal that have both endo and exoskeleton. What do you think? Which animal can have both of them, endo and exoskeleton? Just one animal. Huh? Yes. Exactly. So we have an exception, so the turtle, so it has, as you can see, endo and exoskeleton. So this is just basic definitions to start. Now let's talk about an exoskeleton in terms of technological definition. So what is an exoskeleton? So an exoskeleton is a mechanical frame first. It's a mechanical frame and it is designed to be worn by the human. So human will wear the exoskeleton for each purpose. Why the human should wear the exoskeleton? So it is the design around the function and the shape of the human body. So here, as you can see, you have the human body, then you have an exoskeleton designed to be worn by the human, and the result will be like that. It will be a human wearing an exoskeleton. So this is the second thing to know. Now, when the human moves, he will move with the exoskeleton. So the exoskeleton should move with the wearer by adding strength and durability. So this is one of the purposes of developing exoskeletons, and this additional strength and protection support, it benefits people in dangerous situations, like for workers, for instance, in silent, dangerous situations, or they can be used for mobility issues. So we can use them to restore a mobility that a person do not have due to disability, for instance, or an accident or something like that. So, and also we have to say that exoskeletons, they have been developed initially for military applications, but nowadays we have much more applications and more civilian applications where we are using exoskeletons. So I arrive now to the main applications of exoskeletons, and I can summarize this in this figure. It shows four main applications. So the first one, as I told you, it has been used for military applications. The second application nowadays, which is very well developed, is the application of medical tasks, like rehabilitation, for instance. We have another application for industrial tasks, like for workers in industry. And the last application is for commercial or civilian utilization, like for practicing some sports, you can use some exoskeletons. And now let's talk about the four applications. Let's start by the first application, the medical applications. For medical applications, if we analyze the case of disabled people, here we have different types of paralysis. It depends on the limbs that you lose. In this case, it can be monoplegia, you lose just one member. If it is hemiplegia, just two members like lower and upper, that can be the right or the left side. Diplegia, the two upper members. Paraplegia, the two lower limbs. And the most difficult one is quadriplegia or tetraplegia, with all the four limbs which are not working. And this is the consequence of what we call the spinal cord injury. And as you can see here, it depends on where the injury will happen and the consequence. So I think if it's happened here in the thoracic part, the consequence it will be like a paraplegia, for instance. And so this is just an illustration to start, and just to say that those people, they need help, and exoskeletons, they can be used for this kind of applications. And in general, for medical applications, so these exoskeletons can be considered as assistive devices in physical therapy. This is the main application where exoskeletons are employed, specifically for rehabilitation. And we do rehabilitation to amplify the muscles. I will explain how we can amplify the muscles using an exoskeleton. They can be used to restore a locomotion. So the mobility of one limb of the body is lost, and we want to restore this locomotion to disabled people. So we can use exoskeletons. They can be used for different therapies like stroke, spinal cord injury, and so on. And here we have some illustrations. So we can have exoskeletons of upper limbs like here, it can be lower limbs, it can be like something for training, as you can see in this example, and it can be sometimes for specific parts of the body, as you can see here, exoskeletons for the fingers of the hand. So this is for medical application. Now, the exoskeletons, they can be also good for civilian applications, and they are commercialized. And mainly for this application, they are used to assist humans in daily life tasks. As I told you, sit to stand for elderly persons, it can be very challenging for them. So exoskeletons can be used to help them in daily life tasks, and also elderly persons to do a lot of things like balance or keeping balance, like carry notes, like here rehabilitation, to carry notes using an exoskeleton. It can help the human carry these notes. The third application is for industrial application, and for industrial tasks, the idea is to ease the physical exertion in industry, and this is mainly for workers. And the idea is to force the multiplier, they can use as a force multiplier to increase the force of the unit. Distribute the weight to reduce the user strain or reduce the fatigue, because like in industry, let's take one example. Take this example. Imagine you have a woman working with a tool like that, and the tool, it weighs 10 kilograms, and the woman is using the tool during 8 hours per day. So this is a very big problem. So an exoskeleton can be used to hold here the weight of the tool, such that the human can manipulate very easily this tool. And we have other examples, as you can see here. Here another example, like for car manufacturers. Sometimes you don't carry a heavy tool, but you are in very bad position, like all the day like that, in this position. So this is not very good for the body. You stay like 8 hours like that, it's not good. And exoskeletons may be used as a solution in this context, for instance. And the last application, as I told you, initially, exoskeletons have been developed for military use, and they can be used to protect the soldiers, amplify the strength, increase the endurance, and also improve the efficiency of exoskeletons. And here we have two examples just to understand how they are used. Now, let me introduce a simple classification. Now, if you have to sum up, what are the different kinds of exoskeletons? We have to analyze two things. Or the exoskeleton may be developed for the upper body or for the lower body. So we have two possibilities. Here we have the lower body, here we have the upper body. And for each of them, we can develop either a stationary exoskeleton, an exoskeleton that does not move, it stays in the same place, or a mobile exoskeleton. So if we analyze this, so we have 4 kinds of exoskeletons. The first one is for lower body, and it's static, as you can see here, mainly using for training, for walking, for instance, in rehabilitation. The second example is also for lower limbs, and it is used for rehabilitation, for walking, for restoring motion. And here in this case, it's mobile. It means that the human can use the exoskeleton and it can go away. And you have the same for upper body parts. You can have like a static upper body exoskeleton or a mobile upper body exoskeleton. So this is just to sum up the 4 kinds of exoskeletons. Now let's do better classification of exoskeleton. Let's give you more elements, because the previous classification is very easy, like if it is upper or lower body, and if it is static or moving. Now, if we look at another classification I took from this reference, so they study a very nice classification, and in this classification we can see a lot of things. And here the things are in the columns. So the first column, which part of the body the exoskeleton is focused on. So it can be like full body, it can be upper body, it can be lower body, it can be specific segment of the body, it can be specific joint, just one joint, and it can be other parts of the body. So this is the first thing to know. The second thing is the structure of the exoskeleton itself. So it can be as a rigid exoskeleton, but nowadays we have a tendency to another kind of exoskeletons. They are called soft exoskeletons. So they are not rigid, they are soft, and they are more and more developed in many institutions all over the world. The second classification, or the second criteria, is the action, because actually, for sure, we can have exoskeletons actuated with motors. They are called active exoskeletons, but we have also passive exoskeletons. So they are worn by the human, but they are not actuated. The next criterion is going to be the power technology, how the exoskeleton is actuated, which kind of motors or actuators are used. It can be an electric actuator motor, It can be a hydraulic actuator, it can be a pneumatic actuator, it can be hybrid, it can be mechanical system or others. So this is the actuation of the system itself. And then we have the purpose. Why we develop exoskeletons? So they can be used to as a recovery solution, or they can be used as an improvement or increase in the performance of the human. Like for the case of soldiers, for instance, and recovery, like the case of disability, for instance. And the last column, it shows you the applications where an exoskeleton can be used. So as you can see, it can be the military application, it can be clinical, it can be research activities, it can be industrial, it can be civilian, and other fields. So this gives you an overview about a much more advanced classification, the exoskeleton, regarding a lot of aspects. Now let's talk about control, because I'm interested in developing controllers or exoskeletons. Now let's talk about control. So control, you need to develop an exoskeleton to control the motors or the actuators of your exoskeleton to do a specific task. It can be rehabilitation, for instance, sit to stand, it can be something like that, and we need to develop a controller. So controlling an exoskeleton is not the same as controlling a robotic system, because a robotic system sometimes it can be an isolated system like an industrial robot, and it is there, it's doing the task, and we control the robot, we take into account the dynamics, we take into account what we want to do, the task, the speed, the acceleration, and so on. However, if we are interested in controlling an exoskeleton, the problem is pay attention. Don't forget that inside the exoskeleton you have a human. You have to pay attention to the human inside the exoskeleton. It's not like any robotic system. This is the issue. And this is a typical structure of a control system or a control scheme that can be developed. Let me explain the different parts. Here, as you can see, you have the user, the human is here. Here you have the device, the input-output device. You have the environment, and here we have controller. And we have the interaction between the different parts. And we have, as you can see, different kinds of interactions, mainly three. So the first interaction, it can be like a signal, just a signal. We send the signal from the control system to the actuator. This is a signal, and this is represented by an arrow like that, something like that. This is first. Second, we can have a physical interaction, and the physical interaction, it is represented by this thin arrow. And this interaction, it can be between the exoskeleton itself and the human. It can be between the exoskeleton and the environment, as you can see here and here. And the last here case, we can have both. We can have an interaction where there is an exchange of a signal and also a physical interaction. And now let's focus on the control itself. Control is, as you can see, developed based on hierarchical design, and it means that it has different levels. It has a high level, the mid level, and the low level. Let's explain the three levels. So the high level, it concerns what? It can be considered as the perception layer. It means what? This layer it is used to detect the intention of the human. Like the example of sit to stand, we want to help the human to do this, but how we can detect that the human has the intention to do this? And this is a big problem, and it's not so easy. He will not tell you, okay, I want to go from sit to stand, please activate that. No, it should not be like that. It should be detected automatically. And here you can use like some kind of sensor to detect this intention of the human. It can be like EEG signals, it can be EMG signals, and so on. This is one of the sorts. This is the high level part of the controller, and here we have activity mode and context recognition to recognize what the human wants to do, and it's an identification of the human volitional intent, his intention. Then let's move to the mid-level layer. At the mid-level layer, it can be considered, since you have the high level and the low level, it can be considered as a translation layer. It will translate the intention of the human to actions in the low-level controller. So it's like a translation layer, and here it's what we call intent to state conversion. You can convert this intent of the human to a state of the exoskeleton that should be controlled by this. And the low-level control, this is the classical control, like in a robotic system. When you control the system, you need to design the controller, low-level to control actuators, to do the motion, to do the tracking of the reference trajectories, for instance, and so on. And this is device-specific control, like for robotic systems. And I have just to mention something which is very important here, which is different from any classical robotic system. Look here. You see the user and the exoskeleton and the controller. Pay attention to this word here. Safety, safety, safety. A lot of safety. Everywhere we have to take care about safety because, as I told you, don't forget that you have a human inside the exoskeleton. So you have to pay attention. Now, let's go to the history. I like when I do presentations most of the time to give the history, just to know the origin of developing things. And here let's start talking about the origin of exoskeletons. So it's not very new. For sure, they have been developed a lot in recent years, but these exoskeletons, the idea of using an exoskeleton is very old. So it goes back to like 1890. So this is a patent made by this guy around 1890, and it was never built. It was just like a design drawing, and it's a concept studies to have a human for walking. And this can be considered as an exoskeleton to have a human for walking. Then 1917, we have another exoskeleton here developed by Kelly, and it's operated on steam power with artificial ligaments, like artificial muscles, actuated by artificial muscles. Here, as you can see the design, and it's acting in parallel to the weird movements. So it's in parallel of the different limbs of the human, and it is able to supplement the human power with an external power. This is to help the human to have a bigger power. Then in 1916, another exoskeleton here, it's a huge one. It has 680 kilograms. Just please keep in mind this value, 600 kilograms, and it has 30 degrees of freedom. So it's very strong. It's a full body hydraulically activated exoskeleton, and it's amplified drastically the human force. This is the 60s. Then 1972, another exoskeleton, it's a lightweight exoskeleton developed by a guy. For those who are working in humanoid robotics, how we can guarantee the dynamic stability of walking humanoid robot. So we used a concept that's called CMP, zero moment point. And zero moment point, so it was developed by this guy, Vico Bratovich. And he designed also because he was interested in walking, dynamic walking, and so on. And he developed this exoskeleton around 1972 for assistance in rehabilitation of paraplegic people. So this is the purpose of development of this exoskeleton. And it is actuated with pneumatic actuators, electronically programmed, and the degrees of freedom that are controlled by these exoskeletons are flexion extension in the hip, knee, and ankle. So 3 degrees of freedom here and here and here. And adduction also of the hip. Now, in 1976, another exoskeleton, I do it like that, was developed also. The weight here, as you can see, 27 kilograms. So compared to the 680, as you can see, it's much less here. And it is developed as a walking shed for paraplegic people here. As you can see the illustration here for walking like to upstairs, for instance. And actuated with hydraulic joints, and it works with or without the human load. Turns, walk upstairs, and so on, different tasks that can be done using this exoskeleton. In 2000s, Hokuma developed this exoskeleton, and it is driven gate or voice for electromechanical drives with electrical drives. And the idea is that you have a treadmill, and the human is walking on this treadmill, and just as you can see here, the exoskeleton supporting the lower body of the human. 2004, Blix developed by Berkeley, and it has 7 degrees of freedom, 3 degrees of freedom along the hip, 1 degree of freedom in the knee, and 3 degrees of freedom in the ankle. And it's the first load bearing and electrically autonomous because it has a battery here, and it's autonomously actuated exoskeletons with 4 degrees of freedom, 4 degrees of freedom actuated, 2 in the hip, 1 in the knee, and 1 in the ankle, and actuated with linear hydraulic actuators. Other examples, they come here. 2006, this exoskeleton developed for military applications, and this exoskeleton can amplify by 25 the strength of the person, of the wearer, and it weighs 68 kilograms, and it helps the human lifting 90 kilograms as a payload. 2011, a very successful exoskeleton was developed. It's called Reward, as you can see here, and it's mainly was developed for disabled people. And it's very lightweight exoskeleton, actually with DC motor. And here, as you can see, an illustration where the human is using this exoskeleton, and the exoskeleton it has at the same time physiological and psychological benefits. So physiological, it's very easy to understand this physiological because the human will get this mobility that he lost. But psychological, how can you understand this? Imagine that you have a children and he never walked during his life, and at 20 years old you buy an exoskeleton, you see your son walking for the first time, made some steps. What is the psychological effect or benefit or feeling of the person itself and the family of the person? This is why they said it can have these psychological benefits. And then we have another example from Japan, how they developed different versions, like HAL 3 and HAL 5. Here it has 5 joints activated per leg, per 1, 2, 3, 4, per right part of the body and left part of the body, and it weighs only 10 kilograms. 2018, another exoskeleton developed in Spain by this company. As you can see here, it's used also for walking, the same as the previous exoskeletons. And they developed another version in 2020, and as you can see the illustration here, and it's a powered knee wearable robot for knee extension, as you can see here in the picture, and is activated with a single motor. We have just one motor to activate this degree of freedom in the knee. Now, some examples of exoskeletons of today. The exoskeletons of today, a lot of development we have seen, and we have a lot of examples. And as I told you, the exoskeleton development has started in military applications and in research labs, in universities, in companies. But now we can see some exoskeletons commercialized. You can buy them. For sure, the price is still high, but we can buy exoskeletons. Here's some of them, just to give you examples. A reward that we have presented, so evolved by Reward Robotics. The second one is Exo Bionics, as you can see here. The third example is from Indigo, the same, as you can see, all these 3 exoskeletons almost the same structure, and used for lower limbs, for walking. It can be rehabilitation or restoring the motion. This is slightly different because of the structure itself, because the using, because also the degrees of freedom, because of the weight of the exoskeleton. We have Logomat. Logomat is used like for children rehabilitation, for training or walking, for gait training. And HAL, as I presented before, it can be used for daily life tasks, like carrying heavy payloads. The next one is for industrial applications. As I told you, might be industrial worker working in a company doing something in this position all day. So an exoskeleton like that can be used, and it's very beneficial. It's called walking assist, or it can be used also for walking tasks. The next one is developed in France. It's called Hercule, and it's called the RB3D company. And as you can see, it can help the human carry heavy payloads, and mainly it's developed for industrial applications. Another example from Korea, as you can see, also for industrial applications, carrying payloads. This is for practicing sports, exoathlete. Another one for industrial applications for workers, it's called Fortis. And the last one here is for also practicing sports, and it's called game. Nice. After this presentation of the history, what has been done, the beginning of exoskeletons, and the exoskeletons of today, let me talk about our research. So actually, I'm working in cooperation with the University in Paris. And in that university, so they have exoskeletons. One of the exoskeletons we start working on, it was this one. So as you can see, the exoskeleton itself, it's not very difficult. I mean, the structure itself is very easy because we are talking about the rehabilitation of just one degree of freedom of the leg, and it is for the knee. So it is developed at this research laboratory called DC at UPenn University in Paris, and mainly it's developed for knee rehabilitation. The purpose of using of this exoskeleton is for knee rehabilitation. Now, if you want to do the control of this exoskeleton, first of all, you need to compute or to know the dynamic model of the exoskeleton and the wear. And to compute the dynamic model, for sure, it's easy because it's just 1 degree of freedom, but it's difficult because of, for instance, when you take into account the leg of the human, we cannot know perfectly the leg because it depends on the user. Sometimes you have a user with 70 kilograms of weight or another user with 45 kilograms. So they do not have the same leg, they do not have same weight, same inertia, and so on. So the dynamic itself is not very complex, so it can be written like that. It's just one scalar differential equation. However, the big problem is knowing the different parameters of the system, including the exoskeleton and the wearer. So the human and the exoskeleton together. And how we can identify those parameters. And the other issue is this term, as you can see here, it's the torque developed by the human. The human will develop the torque. Imagine that you have an elderly people who will use this exoskeleton. How you can measure or estimate the torque developed by the human? It's not possible. This is a big issue. Its actuation system, as you can see, it's here. It's a system with a cable, as you can see here, and the two pulleys here, the motor is here, and it transforms the rotation of this motor to a rotation along this axis of the knee. It transforms the rotation here to a rotation along this axis of the knee, and it's mainly used for knee rehabilitation. This is just the hardware of the exoskeleton itself. So the hardware, we have here the control system, we have the power stage, we have the actuators and the sensor that are used here, and we have the signal conditioning system, and this is mastered by this phase control system. Typical applications where we can use this exoskeleton. So as I told you, just for 1 degree of freedom, just for harmony. One of the applications can be the one illustrated on this picture. Just sit to stand, going from this position to this position within this exoskeleton. So this is one application. And another application is for rehabilitation. Imagine that you have a human and you want to do the rehabilitation of the leg, and you have to do a flexion extension of the knee like that, and you repeat this motion. And to repeat this motion, you need to wear the exoskeleton, have the human on this sitting position, and control the motion of the exoskeleton to have this repetitive flexion extension motion. Now, proposed control solutions. What we developed as controllers for this case. So we developed different controllers. Here you have the summary. I will not have the time to detail all the controllers, but I will try to detail only two. So the first one, it will be an error adaptive control, and the second one is a model predictive control. And for these two controllers, they have been so validated in different situations of rehabilitation tasks. Now, let me talk about what we did as rehabilitation. So we have been interested in 3 kinds of rehabilitation. So the first one is called the passive rehabilitation. Second one is the assistive rehabilitation, and the third one is assistance as needed. Let me explain the 3 of them. First of all, don't forget that this exoskeleton has been developed for knee rehabilitation. Let's talk about passive rehabilitation. Let me give you an example, a complete example. Imagine you have a person who had an accident in football, for instance, and he didn't move his leg for 2 months because he has not removed the leg. What will be the consequence? After 2 months, what happened in the leg, and especially in the muscles? He will lose the muscles. He will lose the muscles. They will be very, very weak because the muscles are here because they are moving the different parts of the leg. And if you stop the part, I remember I had this student like many years ago. He didn't move his arm for maybe 2 months, and he lose the muscles of the arm. This is big problem. So you lose muscles, now you have to restore the muscles. How you can restore? You cannot ask a human to, from the beginning, do a hard no. You will destroy the muscles. Yes, what you have to do is to start with something soft, something easy. So we do what we call passive rehabilitation. It means what? It means that we will ask the human to wear the exoskeleton, and as you can see in red, it's the motion by the exoskeleton. The human will not develop anything. Just with the exoskeleton, stay like that. And the exoskeleton start doing this motion of flexion extension, and the muscles will be straight. But the problem is using the passive rehabilitation, this is not enough because you can straighten muscles, but you can arrive to a certain level where it's not enough. You have to do more. And in this case, you will move from passive rehabilitation to resistive rehabilitation. What is resistive rehabilitation? In this case, you have this illustration here. We have a motion, it's the same motion of flexion extension. However, we ask the human to apply an effort, to apply a torque, and the exoskeleton will go against the human. It means what? A human try to develop a torque, but the exoskeleton try to resist. It means that the exoskeleton will incite the human to develop more torque. This is why this resistive rehabilitation will help to strengthen more the muscles of the human. So this is the second one. And the third one, assistance as needed, because we need to help the human. This is the example that I explained before. Imagine that you have an elderly person that cannot do sit to stand, just this. So the human will build the exoskeleton, and the idea here is first, you have to detect the intention of the human. The human wants to go from sit to stand. And the second, we have to help the human. Imagine that the human needs 20 Newton meter added torque in the knee to do sit to stand, 20. And imagine that the elderly person developed like 12. So you need 8 Newton meter as an added value to this torque, to do this motion. So the problem here is to detect the intention of the human, one, and the second is to complete the torque developed by the human to reach 20 Newton meter to do this motion. And this is what we call assistance as needed, and you have here an illustration of this task. Now, fine. Now let's talk about the two control schemes that we developed. So the first one is an L1 adaptive control, and the second one is further predictive control. Let's start by the first one. What is an L1 adaptive control? L1 adaptive control is a recent developed controller for certain purposes compared to classical adaptive control. I will explain the reasons. So we published this paper, and we developed this controller as a flexion extension of the knee, as an application for the knee rehabilitation, and the human is in a sitting position like that. Let me tell you more words about L1 adaptive control. This is more theoretical. I will try to go quickly, but I will try to explain also the concept, because the concept itself is good to understand. Why L1 adaptive control? I think anyone here knows what is L1, what is adaptive control in general first. You know PID control. PID control, so you have like 3 gains. I don't know if you can write. Is this a table? We can write it? No. What? I don't know.
A ver si estas funcionan.
Si se puede apuntar.
¿Se puede reír?
Sí, son de los que se borran. Sí.
Si no, ya nos queda recuerdo.
También acá hay otros.
De lo que es solo los
So let's explain the basic principle of adaptive control. So adaptive control. So imagine that you design here the PID. Here you have your system, and you close the loop here, and you control your system. The first thing is to design the controller. The first thing is to do the tuning of the gains of this controller, such that you have a certain performance of the closed loop system. So if you have a system and you know perfectly the system that works well, and you tune the gains and everything is well, you have. However, if you have something that may change here, or disturbance or parameters of the system that may change, or you can tune the gains based on a model, but the real system is different and so on, you may lose the performance here. So to be able to keep the good performance, whatever the modification, even if you have disturbance or modification of the parameters of the system, we can develop an adaptive controller. So the idea is very easy. You like the idea of model reference adaptive control. So the idea is to have here a model. And this model is the ideal one. Ideal, so you know you want that your closed loop system, the performance will be here. And this system will be, your closed loop system should be all the time close or very close to this model. So you compute the error between the two models, your closed loop system and the reference model. And here is the adaptation mechanism. And you come here to adapt the parameters of your controller. And you do this in an automatic way. So it means that if you have some parameters change here, you have the adaptation mechanism that will update automatically the gain of the PID, such that the parameters, the performance of the closed loop system is still the same all the time. So this is adaptive control. This is classical adaptive control. Now, this idea of using or designing the control like that, it has some drawbacks. What are the drawbacks? First of all, when you do the estimation here you do like an estimation. It's going to be the estimation of the parameters of the controller directly. This is direct adaptive control, or the estimation of the parameters of the system used to compute the parameters of the controller. And this estimation will be done online of the parameters of the system. And this estimation should converge quickly. And to converge quickly, you have what we call the adaptation gain, which is here, and you need to increase it to converge quickly. But the problem, if you increase and you take very high values, you may have oscillations. And this is one of the consequences. This is one problem. The second problem, when you do the estimation, the parameters, what would be the initial value? Just imagine that you don't know the parameters, and when you initialize them, if you put everything to 0, maybe it will not work. And this is the second issue. So we have the issue of the estimation of the parameters, the issue of the initialization parameters, and also the issue of the convergence of the estimation. And this depends on the reference trajectories. So if you do not have trajectories rich enough in frequencies and that's excite enough the parameters, they will just converge. So we have three issues. The gains of adaptation, unity of stability, the initial value of the estimated parameters, and the persistent excitation of the parameters. So L1 adaptive control has been proposed to resolve the three problems. Here, these are the three problems I'm talking about, and it goes through the decoupling, the robustness from adaptation, and the consequence is, in this case, you can initialize your parameters at 0, no problem. They will converge, no problem. So the second gain that we will have, we can increase the gains also. There is no problem of instability. And the third benefit is no need of excitation persistence. So any trajectories, it will be okay. And all these aspects, we can find them in the concept of L1 adaptive control developed like around 2010. And briefly, the concept, it was a lot of applied for aerial systems, aerospace. And the concept is here. We have the control system, we have the state predictor, we have the adaptation mechanism, and we have the key development part of the controller is a low pass filter. And when you introduce this low pass filter, you can increase the gain, no problem, you will not have instability. Basic principle going from multi-reference adaptive control to L1 adaptive control. First stage, you have to replace the reference model. Here, reference model, you have to replace it by actually state predictor. Then second stage is to add this low pass filter, as you can see here, to filter the control input. And the last stage is to add to limitate the estimated parameters, because when you estimate, how you can guarantee that the estimation will not go to infinity? So you will need to guarantee the boundedness of the estimated parameters, and in this case, you have just to add this projection. And the projection added in the control system here. Yes, here you have projection to limit the estimated parameters. Nice. This is just the same block diagram for multi-variable, multi-input, multi-output systems. And here we have a short problem, a small problem with L1 adaptive control. Since you have a filter, and also we have the same for multi-reference adaptive control, if you have a fixed reference like that, you can convert perfectly. But if you have a time-varying reference, you will have a problem of time lag limitation. And this is a limitation for the L1 adaptive control and also for multi-reference adaptive control. As you can see here, you want to track this red reference trajectory, and the blue one is the real one, and you have a time lag between them. So you cannot have perfect convergence to the desired value of the trajectory. So the solution that we propose is just to add an external control loop based on a PID, for instance, and you combine this with the L1 adaptive controller to resolve this problem. And the result will be here, as you can see. If we go back to the example, this is the result. As you can see, the red curve is the desired, the blue is the previous case for the L1 adaptive control, and the gray one is the proposed controller. It's an extended L1 adaptive controller, and we reduce this problem of time lag that we have in the system. Now, experimental results. So we implemented this controller on our exoskeleton, and let me show you some experimental results. So we did experimental results on a healthy person, 65 kilograms weight with 1 meter 78 centimeters, and we did different scenarios. We employ here EMG signals to measure the activity of the muscles of the leg of the human. And we did different scenarios that I will present in the following. We have a scenario where it's the passive rehabilitation, so the human will not develop any torque, any effort, and it's the exoskeleton will do this. The second scenario, assistance as needed, here is to help the human. And the third one is the resistive rehabilitation. And in the following, I will show you just the two scenarios, assistance as needed and also resistive rehabilitation. Let me show you the first scenario. And in the first scenario, this is the obtained results. This is the classical adaptive control. As you can see here, the first curve, it shows the angle of the knee, the evolution of the angle of the knee. It's a flexion extension profile, this motion in a repetitive way. In red, it's the desired trajectory, in the blue is the real one. And we have the speed. The speed of this motion is the velocity. And then we have the torque developed by the exoskeleton. And here the two last signals, they represent the activity of the muscles of the human measured by the EMG signals. When we see this scenario, we can distinguish two parts. We have here the passive rehabilitation. This is the active rehabilitation. Here, as you can see, the human will not develop any efforts, and there is no activity. There is an activity here. And same for the torque. When the human develops, look, as you can see here, the human is developing torque. It means that the exoskeleton will have a lower torque. And here we have more torque because the human is not developing any torque. We have a time lag in the tracking here, as you can see, because it's the classical adaptive control. We have the flexion extension that can be measured through these signals from EMG sensors. And this is the estimated of the parameters in the adaptive control. And as you can see, there is a strong discontinuity in estimated parameters. And this is the big issue that we have to pay attention because it's not good for the actuators of the system. Then we tried our proposed controller, the extended adaptive controller, and you have the performance here. As you can see, it's much better. The tracking, we can distinguish passive and active rehabilitation. We can see that there is no time lag. We can see the flexion extension through the measurement of the signals from the EMG sensors, and we can see the estimated of the parameters without any discontinuity in the parameters information. Then the third scenario is resistive rehabilitation. In this case, we implemented also the adaptive controller. We can distinguish passive and active here. We have time lag here. We have flexion extension measured by the sensors, and we have estimated parameters. And we can notice that we have here some oscillations like a charging in the estimated parameters. And this is also not good for the actuator of the system. So we try to implement our controller also for this scenario. The augmented or extended adaptive controller. And as you can see, the performance is much better. The same, you can see the different phases, passive and active here, estimated parameters, and also there is less oscillations in this case. I have a short video that shows you the obtained experimental result for flexion extension of the knee. By doing experiments on the healthy people, it was the student himself who did the experiment by himself. So he will the exoskeleton and he tried the proposed controller. Here we try to lock the knee first and then we release to go to the desired position, and we repeat this motion by the human. As the details of this developed controller can be found in this conference paper. I will show you by the end of the lecture where you can download our papers already published, and you can see the results or more details about the controller and the results in the paper. The second scenario here is a flexion extension. So we go from this position to this position, we repeat this motion. It's a square signal like that. It means when we arrive, we stay here because it's like that. Then we move to the other position, we stay, and so on. We repeat the same motion. This is second scenario. And the third scenario that we will see in the following sequence, here it's a continuous signal. It's a sinusoidal tracking signal. It moves from flexion to extension, we repeat the motion. And this is the obtained performance. So this is the first controller. Let me now go to the second controller. MPC or Model Predictive Control. And for this controller, we developed, it was published in this paper. You can find the details in the paper also. And the idea here, it was not a flexion extension for sitting position. It was for walking rehabilitation. And we were interested in a scenario for persons who have abnormal walking. What is an abnormal walking? It's not a normal walking. It means that we have two parts, the right and the left one, and the human work like that. So this part is normal, but this is not normal. So working in this way, this is the idea. And we want to do, we want the human will be exoskeleton in this leg and do the rehabilitation to reproduce the normal work. This is the idea. This is the trajectories of the knee for walking, normal and abnormal. As you can see, the normal one should be like that. And this is the red one is abnormal. So when he walks like that, so to be, you don't move correctly this leg. This is when you have less amplitude in the signal. And the default controller is here summarized. I will not go through the details, I will just summarize. So in this case, what we have here the environment, we have the wheel, we have the exoskeleton. In green, it's the parts of our development platform. So we have here an estimation of the parameters. As I told you, pay attention. We need to estimate the parameters of the leg of the human and exoskeleton, both. So this is done here in estimated parameters. We have a first closed loop controller, is nonlinear state feedback controller. Then we have another predictive controller in cascade, second controller. We have here a nonlinear disturbance observer. And you know why we developed this? We developed a nonlinear disturbance observer for the estimation of the human torque. I told you we cannot measure this torque. And we estimate it using a nonlinear disturbance observer. And here, as you can see, the estimated value of this torque. And the last part is here on the top, and it represents the stability of the closed loop system using Lyapunov arguments. So in the following is the equations and so on. I think I will skip this, unless if you want. It's the details of the controller. This is the identification of the parameters. This is the values of the estimated parameters on 3 subjects. Then we develop our input to state feedback linearization, a nonlinear controller like that. This is the second part. Then we develop the proposed by other predictive controller. Here you have the code version of how to minimize to have the constraints. And we developed 2 controllers, a classical model predictive controller and explicit model predictive controller. Explicit, it means it takes into account the constraints, like the constraint in the torque of the motor, for instance. And this is the last part, nonlinear disturbance observer for the estimation of the human torque. Experimental results to finish. So we have a short video that shows you the obtained results and compare the proposed controller, which is an explicit model predictive controller, compared with the PID and the classical model predictive controller. It's just short video talking about this abnormal working. So as I told you, he's talking about this. And we were interested in doing a rehabilitation for a person who has this problem. The only thing is we didn't do experiment on a real subject, a patient. It was on a human because it was so difficult to get this opportunity to do experiment on real patients. I will explain why. Here the results, the PID, as you can see, the track is not so good. Model predictive controller MPC is better than PID, but the best one is here, it's explicit model predictive control. And as you can see, the human is working on a treadmill and using its exoskeleton for the rehabilitation of the knee. Here you can see the signals measured by EMG sensors, and here it's just the verification of the power of the motor used in the exoskeleton, just to quantify the energy used for this rehabilitation. That's it. Let me conclude my presentation and arrive to the end. So the topic of the presentation of today was about the control of wearable robotic systems or exoskeletons. So the idea is to learn about those systems which are used for a lot of applications, and we have mainly 4 applications like military applications, medical applications, industrial applications, and civil applications. So in our case, to develop controllers for these kind of systems or this kind of robotic systems, we were facing a lot of challenges because, as I told you, dynamic model of the leg of the human, you cannot know it. The parameters may change, and it has highly nonlinear dynamic, and also there is the interaction between the human and the exoskeleton, and also the problems of safety that we want to take into account. We need to take account when we do this. We prepare control solutions. I try just to introduce 2 of them, which was the aerodynamic control and the model predictive control, and I show you some experimental results of validation of the proposed control solutions. And the last slide to finish, just some links. I told you that you can find all of our papers online. So okay, they are here. So you can go on ResearchGate and you can download all the papers that you want. So all of them, the preprint of the papers are there. You can download the PDF and you can look through the details of all the proposed controllers. I also here, just if you want to see more about my research activities, so I have a YouTube channel here where you can see like near 100 of videos of experiments, not only exoskeletons, but all the other topics I'm working on. It means the underactuated mechanical systems, underwater vehicles, humanoids, parallel robots, and so on and so on. So a lot of videos here, you can show them. And by this last slide, let me stop here and let me thank you very much for your attention. If you have questions or remarks or comments.
Preguntas, alguien aquí o por aquí.
Thank you very much. Thank you very much, Professor, because yesterday I was in FIME, but today was very presentation about exoskeleton control.
Because yesterday the presentation was about all my research activities. This is why it was short about exoskeletons. But today it's focused on exoskeletons. This is why you have more details.
Yeah, thank you very much for that. Well, I have some questions about the control scheme. I know that the experiment was for monthly operating.
Yeah.
But what about with complex joints, like 2 or 3 degrees of freedom?
Yeah.
What about the schemes? I don't know, the MPC. What is the main challenges? And also, what can you tell us about, if you have tried yet, the interaction with the forces of the human body with the joint?
Nice.
The interactions, like, are you trying it like perturbations or like inner changes?
Yeah.
And what about the interaction with the environment, with the
Nice. Nice. Very good questions. So let me go back just to, or maybe I don't need the slides to explain. So the first question regarding the complexity. Actually, yes, here we did just for 1 degree of freedom. Now, if you want to control or to design other exoskeletons with more degrees of freedom, so for sure the dynamic model will be more complex. One. Second, the control itself will be more complex too. So if we continue developing the same kind of controller, I mean with this structure, I think there will be no problem. Just the idea is how you generate the reference trajectories to be followed for the for walking.
Yeah.
Imagine that it has like 3 degrees of freedom per leg. You have 3 and 3, 6, or you have 5 and 5, 10, for instance. You have to generate the reference trajectories, but for the tracking itself, for the controller, there is no problem. I mean, 1 or 10 degrees of freedom, is the same concept can be developed. Because one of the big problems of modern predictive control, like especially for nonlinear case, is the computation time. If you resolve an optimization problem based on a dynamic model which is more complex and you do the prediction, maybe it will not be useful or not useful. It will not be possible to implement it in real time because of the real-time constraint. But in our case, it's not the case because the controller itself is linear, and we have a nonlinear state feedback controller. So it's still be able to implement in real time. We will not have this problem of computation time. And also, since we have a computer, it's not microcontroller. So we have a computer with enough power to implement the control. Yes, sir.
But your modeling approach is with 2 open chains for each leg. Still.
Yes, actually, it's open kinematic chain, and it's just for the
Not a closed chain.
No.
Okay, good.
Yes, okay. But you are right. I will arrive to this. For the moment, we didn't take, and this is for the second question, which is related also the interaction. The interaction is considered as a perturbation. We didn't model it because first it is very difficult to model it. And when we model it, we have to identify its parameters. If it's like a spring mass model, for instance, how will you identify the parameters of this spring, for instance? And this is not so easy. So we consider it for the moment as a disturbance. This is the second. And for the interaction for walking, you are right. Because when we are walking, it's a periodic motion that we are doing, and we have the interaction with the ground. And the interaction with the ground, when the leg touches the ground, this is the impact phase. We have the double support phase where the two legs are in contact with the ground, and this is like a parallel robot. And we have to consider this closed kinematic chain, so it will be more complex. In our case, no. We just focus on the knee rehabilitation. We try to control just one leg because the other leg is not wearing an exoskeleton, just one wearing the exoskeleton, and we focus on this. But for sure, if you want to do the walking or the whole body or all the joints, yes, you need to take into account this. Take into account the interaction with the ground. You have to. We have the possibility to measure, for instance, the forces, because when we are walking, as I told you, if you want to use the CMP for dynamic walking, we have to measure the contact forces with the ground and to see where we switch. Because when we are walking, I finish this step, I have to move like this leg. And how I detect that I arrived at the beginning of this? I should detect by something. So if I using FSR, force sensors in the leg, I can detect this, or I can measure the position of the CMP. So if the leg is like that, the CMP is here. When I move forward, the CMP will move. When it arrives here, I switch. It will move to the other foot, and I will do the swing phase and so on. So we need, for sure, it's more complex. We need more measurements. We need to take into account the complete dynamics, the closed kinematic chain, and further measurement. And for the interaction, as I told you, yes, we can take it into account, but it's more complex.
And what about the center of gravity with the body, the changing?
It will have an impact on the interaction with the ground, because on the knee itself, it has not an impact. I mean, you are walking like that, or like that, or like that. The knee do the same. But for the interaction with the ground, for sure, if you are doing like that, the CMP, it will be not in the same position. And also the center of mass, center of mass and the CMP. If you are doing dynamic walking, you have to look to the CMP more. If you are doing static walking, but it's not the case, human are working dynamically, so it will be the center of mass.
Thank you.
Yeah, please.
I have a question that's in my mind that told me to ask you.
Yeah.
How do you evaluate intervention, an external evaluation of using or the need of an exoskeleton, and now working with the nervous system, the thing that is Neuralink doing right now to use chips? Yeah. How do you make the evaluation? Because I know the exoskeleton is always can be used, but it is need to be used, or it's another intervention like working with the hardware and with the software, the brain, and not the hardware that the exoskeleton to help the body.
I can show you a short video. It's not our work, but it's the work of a company in France. And let's be just.
En FIME tenemos trabajo sobre eso. En FIME hemos trabajado sobre el control de exoesqueletos con señales electroencefalográficas. Si quiero lo tenemos avance.
Yes, of course.
Yes, just to answer the question, so this is a work of a company in France. It's called Climatech, and they are developing this solution that we are talking about. So this is the exoskeleton. So they develop this exoskeleton, and here they develop the control system of the exoskeleton based on EEG signals, and they analyze the activity of the brain, and they develop a small device that can be fixed here on the head of this one. And they measure, yes, and they measure this. They measure this activity and they connect the activity of this device. It's connected to the exoskeleton here. As you can see, the information is sent here to the control system and so on, and they are moving the exoskeleton. And this is the real exoskeleton, as you can see. So, but in our case, we didn't use yet. This is the controller. The transformation of the solution of the it's also the same as we are. Yes. Other questions or remarks or comments? Thank you very much.
We want to make everyone recognition. Yes. Yeah. From Iceberg to Square, the Royal government, we want to make this recognition, Dr. Ahmed, and thank you very much for your knowledge and sharing with us your experiences and all the development you have been working in exoskeletons and other fields we can see it before. Thank you very much and bienvenido a México.
Thank you very much.
Damos por cerrado los trabajos, ¿no?